Hey everybody, thanks for checking into yet another math video, another one on logarithms even. This one's going to be kind of a two-part video. We're going to talk about some log identities, and then we'll show you how you can use logarithms to solve equations. All right, it's very, very useful and practical application of using logarithms. All right, well, let's first talk about some of these log identities. And I want to keep in mind here this relationship between a log equation and an exponential equation. They both mean the same thing. One of them on the left is solved for y, and the one on the right is solved for x. But log base b of x equaling y is saying the same kind of thing as b to the y equals x. The two equations really basically say the same thing. All right, let's keep that in mind as we look at these. Here's first identity, log base b of b equals 1, all right? And that's very straightforward, I think, for most people. Thinking that as b to the 1 equals b makes it pretty sensible. Here's a couple of examples. Log base 10 of 10 equals 1. Log base 2 of 2 equals 1. All right. So that one is a pretty easy one to understand. It does not matter if what the base is. If the base and the argument are the same, then that logarithm equals 1. Here's another one, very, very straightforward also. Log base b of 1, when the argument is 1, that logarithm equals 0. All right, and it doesn't matter what the base is because any base, any number to the 0 power equals 1. All right, the next one is a little bit more complicated looking. Log base b of b to the x equals x. This one actually is, it's not too bad. It looks a little more complicated, but when you think about it this way, for example, log base 3 of 3 to the 5th equals 5. That's because when you kind of unwrap that log expression, you get 3 to the 5th. And so it's just saying 3 to the 5th equals 3 to the 5th. Or the other one there, log base 10 of 10 to the pi equals pi because 10 to the pi equals 10 to the pi, all right? That's kind of a weird example there, but we can think of this in a little bit different ways too. For example, log base 2 of 1/2. Well, if you thought of the 1/2 as a power of 2, power of that same log base, then you would probably come up with this, log base 2 of 2 to the negative first, because 1/2 and 2 to the negative first are the same thing. Well, that maybe explains why then that equals negative 1. Or if you had log of 10,000, log base 10 of 10,000, 10,000 is 10 to the 4th. So if you have log base 10 of 10 to the 4th, that equals 4. All right? So that identity there is actually helpful sometimes in evaluating some other log expression. So keep that in mind. If you can get the argument of the log expression to be the same base as the base of the log, then the exponent there is just what that whole logarithm equals. All right? All right, so this last log identity is kind of a head twister here. It's a strange little expression. B to the log base b of x equals x. This is an odd little expression. You don't see it too often, but you do see it sometimes. So I thought I'd try to explain why this one equals. If my explanation just kind of whooshes right past you or is just too weird, don't worry about it. Maybe you can just sort of remember how this thing looks and apply it whenever you need to. But here, let's take a look at the exponent there, log base b of x. Well, if you interpret what that means, all right, that exponent means it's the exponent itself represents the exponent of b that gives me x. Log base b of x means the exponent of b that gives me x, right? Well, what I'm doing is I'm taking b and I'm raising it to that power. So it's b raised to the power of b that gives me x. Well, if I raise b to that power, then it must give me x, right? I mean, that's the only thing it can equal. It's a weird thing. It's kind of like saying the same thing twice inside of itself. It's a strange thing. Actually, I don't need that exclamation point there. It's not a factorial. So anyway, that's the fourth log identity. It is an odd little expression sometimes, and you may see it sometimes, but it's kind of rare. All right, so let's move on to the second part of the video here about solving exponential equations with logarithms. Before we talk much about this, first thing that I want to say is that An exponential equation is any equation where the unknown variable that you're solving for is an exponent. So if you're solving an equation to try to figure out what the exponent of something is, that's when you'll use logarithms, and that's the only time that you'll use them. You don't use logarithms in any other case for solving an equation, only when the variable you're solving for is actually an exponent, okay? And the reason for this is that log functions and exponential functions are inverses. As we've said many times, they are inverses of each other, which in here, what's useful to think about them is that inverses are functions that undo each other. So one function undoes the other one, and that's why they're useful in solving equations. As a matter of fact, you have always used inverses to solve equations, right? Here, let me show you what I mean by that. You've always used inverses to solve equations. Like here's a simple equation, x plus 3 equals 5. Well, how do you solve that? You solve it by subtracting 3 from both sides, because subtraction is the inverse of addition, all right? Here's another one, 3 times x equals 5. You solve that one by division, because division is the inverse of multiplying. 3 times x is multiplying, so you undo that multiplying by using division. Here's another one. Square root of x equals 5. Okay? Well, what's the inverse operation for taking the square root? Well, it's squaring, and that's how you solve this. You square both sides of the equation, and you get your solution for x. X equals 25. All right? So it's always true that you've used inverses to solve an equation. But if you have an equation, even just a really basic, simple-looking one like that, 3 to the x power equals 5, well, what is the inverse of raising to the power? Actually, that's called exponentiating. What's the inverse of exponentiating? It's logarithms, okay? Logarithms undo exponentiating, all right? So what we're going to do to solve this equation is then just take the log of both sides of the equation. All right, so I could write it like that. It's a very simple, straightforward thing. I'm just taking the log of both sides. You'll find that this process, even though it may seem strange at first, is really, really simple to carry out, okay? The process isn't very lengthy or complicated. So I start off by taking the log of both sides. So everything's cool. I've done the exact same thing to both quantities on both sides of that equal sign there. So the equation is still the same equation. I'm taking the log of both sides now, and now I can use one of those log properties that we had, the wraparound rule or the power rule, to write that as x times log of 3 equals log of 5. Okay, so I've got x times a number equals another number. Well, all I got to do now is divide both sides by log of 3, all right? Divide both sides by log of 3, and I get x all by itself. It equals log of 5 divided by log of 3. Now, log of 5 over log of 3, that's what we would call the exact value for the solution to this equation. It's the exact value. You may at some times want to use a calculator to get an approximation of this value. So I'm putting this in here for you to check. This is the approximate value of log 5 divided by log 3. Now, I really would like you to try this out on your calculator to see if you can get your calculator to give you this value here. I can't even tell you as a math teacher how many times I've seen people do the right algebra but then mess up on the calculator, and they don't really realize it, because if you make some of the mistakes that people make with doing this, the answer isn't that much different. It sort of seems like can be in the ballpark. So try this out and make sure that you get the right value there. That'll tell you if you're using the right sequence of keys on your calculator. Okay? One more thing about this, since we're talking about possible mistakes, is that log 5 over log 3 does not equal log of 5/3. All right? The logs do not cancel out. Don't even think of trying to cancel out the log on both sides of that, both the top and the bottom of that fraction. That's not what's going on there, okay? It does not equal log of 5/3. It does not equal just 5/3. It's just log of 5 over log of 3, and there is no other way to write it other than to use an approximation of it from a calculator, okay? So if that's confusing, go back and take another look at that video about the log properties to make sure that your understanding of that quotient rule of logarithms is being followed here, okay? So I know this is a place where a lot of people get confused. So that's why I put that in there. It's an important little point here for you to make. Let's try one more here. This will be like a word problem or an application problem, a situational problem we're starting to call them now. I got $50,000 in a bank. Yay, I'm rich. And it's growing at 3.5% per year. And I would like to know, how long will it take for that $50,000 to grow into $70,000, assuming no financial catastrophes along the way? So if it just keeps growing, how long will it take? All right. Well, here's an equation that you may have you may have had some practice writing equations like this. These exponential growth rate equations. 50,000 times 1.035. That is what 3.5% growth translates to as a decimal value. 1.035. So I'm taking that 1.035 every year. So in other words, I'm raising it to some power of years, so many years. And my $50,000 will grow into $70,000. I'm trying to solve that equation now for the exponent t. Well, the first thing I have to do is isolate the exponential part. I can't take the log yet because I have to get that exponential part kind of isolated all by itself. So, but that's pretty easy here. I'm just going to divide both sides by 50,000. A bunch of things cancel out and I get this 1.035t. I don't know what happened to my decimal point there, equals 7 over 5, which is 1.4. So let's tidy that up. 1.035 to the t power equals 1.4. And now I've got the exponential part all isolated. I can take the log of both sides of this equation now. Log of the left side equals log of the right side. And let's see, then I'm going to use that wraparound idea with the log property, the power rule. I got t times some number, log of 1.035, and I'm just going to divide both sides once again, and there's my exact expression for how long it will take. Can you look at that fraction and tell me about how many years it's going to take for $50,000 to grow into $70,000? Because I can't. I have no idea really what that fraction equals until I actually try it out on a calculator. Turns out that it's about 9.8 years, okay? So I'm going to have to wait a while for my $50,000 to turn into $70,000, but that's okay. So here's a place where using an approximate value would really be the right thing to do, all right? So you kind of have to make a decision there whether you're going to use the exact value for your solution or in a more practical approximate solution. All right, well, let's summarize this stuff here. To solve an exponential equation with logs, the first thing you need to do is to isolate the exponential part of the equation. All right, and once you do that, then you can take the log of both sides, and only then. And after you take the log of both sides, you'll use that power rule, that wraparound idea, to get the t value there, or the x value, whatever variable it is, all by itself. And then you divide and you can get your solution pretty easily from there. So that's basically the process right there. The only thing else I would say is that you need to choose the best form for your solution, whether exact is appropriate or whether approximate is appropriate. All right, and that's going to be depending on the type of equation. And as always, be careful with your calculator. Okay, well, that about does it for this video here. Thanks very, very much for watching. I hope you're well. All right, so stay smart, stay cool, do some good math, and I hope to see you soon. Bye-bye.